All right, so last time we talked about graph traversals. Okay, so what was a Hamiltonian traversal? So Hamiltonian traversal, as you've just told us, was a traversal of a graph where each vertex was passed through exactly once. So we have the notion of a Hamiltonian path. What is a path, by the way? And then that of a circuit. So what is a path? Path. How did we define a path?
It's like a set of edges that you traverse to get from one vertex to another.
That's exactly right. So we defined it as a set of edges. We can list also the vertices along the path. So here's an alternative way. Here's let's say we start at V0 and we move to V2 in this particular order. So then we have like V3 and so on, blah, 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 and we get to Vn. Suppose it's a path of length n minus 1. You have n vertices there. Now, if V sub n and V sub 1 happen to be the same vertex, then we say that we are traversing a circuit, right? So these vertices V1 through Vn, yes, I've listed n of them, but they need not be distinct vertices. Okay. So today we'll introduce a notion of a weighted graph. In fact, we've already introduced the notion of a weighted graph, like on day one of graphs. These are simply graphs whose edges have a number attached to them. The number that we call the weight or a cost of the edge, depending on the context. So we have this function w from the edges to the reals. Okay, so what does it mean? W, as an example, W takes an edge and assigns the number like 17.55 or something like that. Okay, so example. So here's an example of a graph. Nothing different from what we've seen before. These vertices represent the cities and the edges represent connections between them. So for example, roads or flights between the cities. Now these flights or roads, or here, these connections have numbers attached to them. So the weight, for example, of the edge, call it Chicago, Boston, that edge has the weight of 860 attached to it. So each of these edges has an attached weight. Okay, so this is exactly what I wrote down here. Okay, here's some edge like Boston to Chicago, or any other edge of the graph, and it has some weight attached to it, like a number, like 1755. Okay, so this is all good. Now, we have a notion of a path. We have a weight attached to each edge of the graph. We can define the notion of a weight of the path itself. So let's call this path P. Okay, so here's this P path, and we're defining the weight of a path. Okay, the weight of a path is defined as simply the sum of the weights of the edges along that path. Okay, so let's write it down. So it's the sum. Let's say I ranges from 1. Let's range it to n minus 1. And here's the weight of the edge v sub I plus 1. Okay, so these weights, the sum of these weights, I have n minus weights because I have n minus 1 edges along that path. They sum up to some number. And that number is called the weight of the path. So here, for example, what's the weight of the path? Let's take something with smaller numbers. By the way, these numbers, okay, so what numbers you attach to the edges depends on the context and the problem at hand. So for example, in this graph here, the weights attached to the edges are distances. Or you can have weights attached to the edges, so the costs of those flights. All right, so what is the distance or what is the cost, for example, of getting from Chicago to Boston? Okay, so you can go and take a direct flight from Chicago to Boston for $79, or you can go from Chicago to New York, and then from New York to Boston for a total cost of $59 plus $39. Okay, so that's 80 and 18, that's 98. Okay, or you can take, given that this graph is undirected, you can think of a variety of other paths of getting to Boston. Okay. Of all these paths that exist in this graph between any two nodes, the problem of the shortest path is to determine that path that has the lowest cost. Okay. So for example, okay, this is, by the way, the same graph, and the purpose of this slide is to show people that these weights along the edges can be anything vary depending on the context. So this time, the weights associated with the edges are the times it takes to travel from one node to another, and so on. Okay, so in this graph, for example, also nodes looks like airports here. This seems to be like Providence. This guy seems to be LA. Here's Honolulu. And the problem here, the problem of the shortest path problem is to determine of all the paths that exist between Honolulu and Providence, you want to find the one that has the shortest, the lowest cost. Okay, so here it looks like the edges here are the distances. So the shortest path route would be like this one, the one shown in red. Of course, there are other ways of getting there, okay? But you want to pick of all these paths, you want to pick the one that has the smallest weight. So pretty straightforward problem. So today we'll discuss an algorithm of finding the shortest paths, the one that lives in your GPS system as you drive around. The Dijkstra's algorithm lives in your GPS. So Dijkstra is just one of the algorithms that works on graphs like this, on connected graphs whose edge costs are non-negative. And actually, let's take a minute to talk about that. Why do we say that the edge costs have to be non-negative? Well, for this particular application where the costs are distances, let's say, of course, the distances are non-negative in this physical world in which we live. Okay, so that makes sense. Or the times are non-negative, that makes sense. But of course, graphs can be modeling other things. Like, for example, in finance, you can be modeling the edges between two nodes can represent, for example, a profit from a financial transaction. In that case, the edges can be negative. And you may be building a graph if you are working for like a trading branch of some investment bank, for example, determining arbitrage opportunities in trades. Okay, if that's the case, then those edges sometimes can be negative, and you maybe the shortest path may represent the path of like a sequence of trades in which you earn some profit or lose money or whatever. So this is just to say that the applications of these graphs are endless. And today we're talking about these applications where the edges have non-negative costs. Okay, so now let's talk about that for just 1 second. So here's an example. Let me draw here. So here you have like V1, V2, okay, V3, let's say, V3, V4. Okay, so that's enough. Or maybe V5. Okay, so you have V5 also. So you have these edges. Let's take direct. By the way, the algorithm that we'll discuss today will work with minor modifications with both directed and undirected graphs. So sometimes I'll draw edges with directions, sometimes without them. That in the end will not matter. Well, suppose let's draw this as a directed graph. So from V1, V2, you have a cost of 2 of getting there. Here you have a cost of -7. Okay, let's say here, I don't know, a cost of like, I don't know, 3. And here you have a cost of, I don't know, -4, whatever. So what's the cost of going from V1 to V5? There's no problem. You can find the cost, right? Just from this definition that we just gave, just simply add up the costs and it's no problem. So what is the cost? The cost, again, is defined as the sum of the costs of the edges. And the costs are assigned simply to the edges. So you just simply know that the cost of going from V1 to V2 is just 2. So 2 and -7 looks like that's -5, and +3, that's -2, and then another -4 looks like a -6 to me. So the weight of this path here, which is a sequence of vertices, V1, V2, V3, V4, V5, the weight of this path, unless I made a mistake here in adding those numbers up, is going to be -6. Okay, that's the cost of the path. Okay, fine. There seems to be no problem with this. But actually today, graphs, the restrictions we're placing on graphs, there are a couple of, okay, must be today. There are other algorithms that adapt to weights that are non-negative. Okay. So can I ask you when what do you think? Like, can you give an example of a graph on like 3 or 4 nodes or any number of nodes? So let's actually have just a general case. You have U, and then you have a bunch of nodes, then you have some vertex S, and then and so on, and you have some vertex V. And this is part of a larger graph. So you have other nodes in this graph. And what I drew here is, what I've drawn here, in this piece here, is just one path of many, possibly middle, between U and V. When will there be no shortest path between U and V? That's the question. When will the shortest path not exist between U and V? The shortest will not exist. Again, the length of the path is defined as the sum of edge costs. So in this graph, there's clearly a path of a given weight. The weight of that path is -6. But my claim is that it's possible for a shortest path to not exist.
Is that when the weights, including negative weights, like add up to be 0?
Well, then that would be, by definition, would be the path of weight 0.
Yeah, never mind.
If you have multiple paths and they're all the same weight, then there wouldn't be a singular short.
Okay, that's a good point. But suppose you get to pick any of those paths. If you find two paths of the same weight, you just pick one. It doesn't matter. Right. So in that case, we say that a shortest path exists. It's just we have not a single path of that given weight, of that weight. So yeah, you can. Yes.
If there is no connection between.
Okay, that is true. The one thing that has to be true about these graphs today, graphs G today, G must be connected. That is true. Otherwise, there's just simply no path between them. There's no way, if the graph is disconnected, if it is not connected, and if there's no path between U and V, then
the other one,
yes.
The other requirement should be that there's at least two vertices
in the graph. Okay, so let's assume G with at least two verts. Okay, so I hope it doesn't sound like a trick question. Here's what I'm asking. So my claim is that if I allow for negative weights, then it's quite possible that the shortest path does not exist. So for example, consider a graph that has cycles in it. Okay, so today we'll talk about no cycles. No negative weights. Rather, so let me say no negative weight cycles. That should be enough, cycles, like that. So for example, if I have these paths, let's take a concrete example. So this works out to, like, I don't know, 5. This is like 6. Let me add like these are different colors. Okay. So let's try this. You have 5. Let's say this is 6. Let's suppose this is just one line. This is, I don't know, 1, 4. Okay, you get there. This is 4. And then I have, like, I don't know, 2, 3, -7, and 1. Okay. I have a path like that is a cycle. So you'll say, like, if you don't go through the cycle, you can go from U to V for the cost of, looks like 10 and 16. For the cost of 16, you can get from U to V. But there is a shorter way of getting from U to V. You get to S at a cost of 11 or whatever it is. And then you go up there, that's the cost, it looks like 5 and -7 plus 1, -1. There's a cost of -1 to get from S back to S. Okay, so I could, conceivably, if I'm allowing these cycles with negative weights, I could get to S, then keep cycling here as many times as it makes me happy, decreasing the cost by 1 each time, and then getting to V. So instead of getting from U to V at the cost of, looks like 16, I can get there at the cost of 15. Or I can get there at the cost of 14. Right? So do people see this? Or at the cost of 13. If I traverse this 3 times and then go to V, the cycle. So I can diminish this cost as many times, as much as I'd like, by traversing this cycle as many times as I need. Right? So today this could happen in a graph that models some circumstance. Okay. But in today's graphs, where the edges are distances or times, or costs like money, the cost of, okay, I suppose you could argue that costs could be like negative too. The airline may be paying you money to go somewhere, but we're not allowing those negative costs. So the edges will be assigned, positive weights, as in the graph shown here. All these weights are distances. Okay, so let's leave this aside. These are the assumptions that we're making on our graphs today. Okay, that's all good and well. Any questions so far? So far, everything's pretty intuitive. The graphs are as before. It's just the new element is that the edges have some numbers assigned to them. Every edge has a number assigned to it that we call the weight of that edge or the cost associated with that edge. That's it. Okay, now let's talk about, I want to talk about an algorithm, one of many, that finds the shortest path from one vertex to another vertex. Okay. So let me first, we'll do a couple of examples today. I want to write down the pseudocode for this, and it's not required in this class, but it's a good exercise. If you have a favorite programming language, just go and implement this on your own. Although, with so many sites available with this code and Dijkstra, there's always a temptation to not do this exercise. I suggest at some point, maybe not now, you may not have time for this now, but at some point you should try to write this on your own. You should implement such small algorithms on your own, like Dijkstra. It's a good exercise to do it. So, but before writing down the pseudocode for this algorithm, I just want to give you an overview, just point by point, how it will work. Will be kind of a I wouldn't say it's going to be vague. I'll try to be as clear as possible, but it won't be clear pseudocode yet. Okay, so I want to give you an overview, then I want to work through the example, and then we'll write down the pseudocode, and then we'll work through more examples. Okay, so here's how it works. So we're going to maintain an invariant in this algorithm. What do we mean? What's an invariant of an algorithm?
Something that never changes through each use of the algorithm.
Yes. Maintain the following invariant. Okay, let me write this down in words. We're going to have a set S of vertices. That is, initially that set is empty, or you can, depending on how you write the algorithm, you can just put one start vertex onto this set S. But this S, the set, so invariant is set S of vertices whose distances to the source vertex is known. So here's what we have. So our graph, just to be clear, so here's our G. So here's some graph. So you have a source vertex here, S, source vertex here, and it's attached to other vertices inside the graph, and then you traverse this graph somehow, and you want to get, perhaps there are multiple edges attached to this final vertex. It's called T sometimes for terminal vertex, and S for start or the source vertex, and T for the final terminal vertex. And you want to find of all these paths that can possibly exist here to get to T. Again, the problem is to find the shortest one of all possible ones. So this set S will have all the vertices whose distances from the source vertex, small s, is known. Okay, the set S of all vertices, so my graph is like VE, all vertices, okay, whose distance to S, or from S, I don't know, so from S, let's use from S, distance from S is known to be optimal. From S, this is now small s, is known to be optimal. Let me just put optimal. That is, you know the shortest distance to those vertices from S. Okay, initially that set is empty. When you start, before you start the algorithm, you don't know the optimal distances from the source vertex to every other vertex in the graph. But as soon as you begin with the first iteration, and I'll describe iterations in a minute, of the algorithm, then you will, for example, you start expanding this set by attaching the distance of 0 to the source vertex itself. What does that mean? Once you attach the source to S, the small s, once you attach the distance, and we'll denote distance, so initially, distance, we'll denote distance to S, or distance, so distance V will stand, distance to V is distance, this is notation, distance from S to V. This is going to be our notation. Initially, distance from, what is that then? Dist S is 0, and dist to every other vertex at the start is infinity. So I do not know what the distances are to all those vertices that are outside of S. So I'm attaching, like, for an unknown, infinite distance to every other vertex. But the set S itself initially is empty, and I keep at every step of the algorithm adding one vertex to this big set S one at a time. Will be clear as we run through an example, but for now, just bear with me with the overview. So initially, the set S is empty. I add the source vertex to it. Then at the next iteration of the algorithm, I'll be adding another vertex to it, and so on and so forth. And we'll keep going. Now, let me just draw a quick picture here while we're at it. So here's again, well, we have here a graph. So let's do it this way. So you have this graph, and here's a snap. So you have a start vertex here somewhere. So you have a start vertex here, call it S, small s. And then you have this set of vertices, we'll call it a cloud, that keeps expanding until it consumes the entire graph G. This is somewhere here is the terminal vertex, to where I need to get to. And I keep expanding this cloud S by consuming at each step one additional vertex. So it is an ever expanding cloud, and it keeps growing and growing until it consumes all the vertices of the graph entirely, consumes the whole graph, and therefore includes vertex T itself. So every time you add a vertex to this ever expanding cloud S, you know that that vertex now that is all that has just been added to S is, you know, the distance to it to be optimal, the shortest one. So initially, when you get started, it's only the source vertex is in it, and the distance from source to itself is going to be 0 to begin with. And every other vertex is going to have an infinite distance attached to it. As soon as I add a new vertex to this S, as we'll see, then I'll change this estimate of an infinity to that vertex to some smaller number. Again, we'll see this in an example. Okay, so this is going to be happening. And then what we'll be doing as we're running this algorithm, we'll be peering out from this cloud, just looking for all these vertices that are attached to the vertices that are already known to be optimal. They're all already inside the cloud. So you're looking outside and looking at the estimates of those vertices that are outside of the cloud. And when we find the smallest estimate, we add that guy to the guy. Let's say this guy is the smallest. Let's say this is the smallest. So now we add this to the cloud, and we keep expanding the cloud like this. At the next step, then I'm looking for new vertices that are attached to this. Let's say there may be like 3 new vertices attached to it. Then I'll be looking at all the distances that are the shortest ones that I can see from S, the cloud, and so on. And then again, we'll do an example. Okay, so first let's continue with these high-level overview steps. Okay, so this will be happening. Okay, you can, by the way, feel free to stop me and ask me if something is unclear. Again, we'll be clarifying many of these things as we go along. This is our cloud S. This is our entire graph. Okay, 2 more things I need to mention. That okay, so just how does this S grows? One vertex at a time. Grows one vertex at a time at each step. Let's call it at a time. Okay, say at each step. Okay, so and the procedure is this, and the heart of the procedure is this. Of all the edges, I could be writing this in pseudocode, but let's write in words. All the edges emanating from S, pick the one that has the lowest cost. Pick the best. Okay, pick the best. The one with the shortest, the one with the lowest cost. The lowest cost. Okay. Okay, that's and add it to S, and add this new vertex to S. Okay, to S. And finally, update the this is the last step, update the distance estimates to the new, to this, well, update the distance estimate to this new vertex. Okay, let's write it to this new vertex, Okay, this will be the heart of the algorithm, which we'll call the relaxation step, and we'll see how. Okay, so we'll see how. It's a simple step, but we'll see how. Okay, now let's run this algorithm. So let's take a moment to digest what we're doing. So we have a graph like this. We want to know of all the paths that exist from S to T. I want to pick the shortest one. I have the computative set, the cloud set that I don't know much about. Initially, it's empty. That will be expanding as the algorithm runs. It will be a set of vertices, initially empty, and we'll be adding at each step of the algorithm one vertex at a time to this set S. First, we add the source vertex and declare the distance from source to itself to be 0, and every other vertex will have a distance of infinity attached to it. Then we'll peer out from this S like that and look at every vertex that can be reached from S. You pick the shortest of those and let S consume that vertex. Then you peer out to other vertices that can be reached from S and pick the shortest. Let S consume that shortest, and so on, until you encompass every vertex in the graph. Now, it's another question, and the claim is that it will work. It will find that this is a greedy approach. So at each step, you're making the greedy choice. You're getting, in the sense that you're getting the vertex that is the easiest to reach at each step. And it somehow, magically, this doesn't always work, but in this problem, it so works out that at the end of the day, this greedy approach of adding vertices this way to the set S will include the final vertex T, and the estimate, the distance estimate to that final terminal vertex T will be the optimal one. It will be the distance that I will declare attached to that vertex will be correct. It will be the shortest path, shortest weight from S to T. Okay, so this is all just talk. Any questions about the talk part? Now we'll do an actual example so that we'll run through.
So basically, you're just doing it by brute force and finding every combination of paths between the two, and then whichever one.
So it is better than brute force. It will turn out that as this algorithm runs, it will not be considering all the paths from S to T. It will be discarding as it runs the paths that it will know for sure in some intermediate step of its run to yield a path in the end that will be worse than it is currently considering. So the short answer is it will not be looking at every combination, as you put it, of all the paths from S to T. It will greedily be selecting of all the available paths, the one that will eventually be the optimal. Does that make sense? So good point, right? So we are not doing an exhaustive search of all paths. That's an alternative approach. And if you consider a runtime of an algorithm that looks at that just finds every possible path, looks at the costs of all possible paths and compares them, the claim is that approach will take longer than the approach that we're about to take. With Dijkstra's, we will not have to consider every possible path from S to T. But we will be selecting of all the paths that exist in the graph, we will be selecting the best in the sense that it will be the shortest. Right? Does that make sense? Just as an overview for now, or no? Right. So it is not an exhaustive search algorithm. Okay. Any other remarks? Okay. So now let me illustrate this now on a tiny example. So we'll do at least 2 examples today. So here's a graph. It's a tiny one. Again, by the way, on the quizzes, I mean, there's no way for me to bring a giant. I mean, there is a way, but I don't want to bring some giant unweightable through graphs, right? You can usually tell if you see a graph on the quiz, you can just by hand see what the shortest path is. That's not the problem. But you will be writing up your solution in a very particular way, which I'll show you in the second example. For now, with this first example, let's just run through this through this particular run, through this small graph. And just by looking, you can tell what the shortest distance is. But again, let's just run the procedure that we just described. So what's the first? So initially this set S. So this is our graph. It has these vertices A, B, C, D, and all the edges as shown there. So let's ignore the coloring of the edges for now. S is initially empty. And now I add, so initially it was empty, and now, so started out S initially is empty. And now I added A to this ever-expanding cloud of vertices. So this is going to be my cloud. Well, that will grow. Will grow. So initially it just has one red vertex. So maybe I should go with red here. This A. Okay. Now I'm peering out of S. I'm looking out. What can I reach? Okay. Also, initially all my estimates to all the other vertices were infinities. Okay. And 0 was the estimate to the start vertex A. What the 0 estimate says is that the distance from A to A is 0. That's what it says, right? Now I'm looking outside. I'm looking at this vertex, and this vertex, right? So looking outside. If I go through this, like this edge, if I take this edge, then the way to reach B will be 8. So I erase that infinity there and place an 8 there as a label. I annotate the vertex B with an 8. I annotate the vertex C, which was originally infinity, erase that infinity, and annotate this with a 2, vertex C. And I do the same here, is annotate this with a 4, vertex D, because that's the way to reach B. Now, these numbers, this 8, 2, and 4, are now my estimates of getting to those vertices that I can see from S. Those are not yet the optimal ways of getting there. Once a vertex, now I'm going to be adding a vertex, according to the procedure we just described, I'm going to be adding a vertex to S. Because at this point, it just has one vertex. Now I'm going to be adding one of these vertices to it. And then once I add that vertex to S, then I will declare that I now know the shortest path from the start vertex to that vertex that I just added to S. And the way I add the vertex, a vertex to S, is by looking at these estimates and greedily picking the shortest one. So what's the smallest number of these? 8, 4, and 2, right? So 2 is the smallest of them. So I let S consume C. So I will just add that vertex C to my set S. So now S will become A and C, and it will continue growing. Okay, so let's see the next slide here. So here I've added this S. Okay, now let's go to the next step. On the next step, I'm peering out of S. So now before I couldn't see these vertices like F and E, they had infinities attached to them. I couldn't see them from there. But now that I've included C into my vertex set S, I can peer out and see F and E as well. And I can see D and B as before, but notice that now I have other ways of reaching those vertices, D and B. So for example, before, my best estimate of reaching D was 4, right? It started out at infinity, I erased that, and now I said that I have a way of reaching it at 4. Okay, so that was good. So at this stage, I know that I can get to D at the cost of 4. But once this vertex was added to the cloud, once C was added to the cloud, I now have a new way of reaching D. And that new way of reaching D is at an additional cost of 1. It's an additional cost. So now the cost of getting to C was 2, and now I have an additional cost of getting to D at the cost of 1, so for a total cost of 3. So what we do is we erase that 4 and make it a 3. Okay, maybe I should put it there. So that 3 got here because we erased the 4, that the cost of 4 that we had of getting to D. Now, what's happening with B? Well, with B, nothing changes because initially the cost of reaching B was 8, I do have another way of reaching B. But notice that this edge here is dashed. Why is it dashed? As is this one, by the way. This is called, we're relaxing those edges. It's called this is called a relaxation step, but more on that later when we write the pseudocode. So here, a way of reaching B is at an additional cost of 7. But now 2 plus 7 is 9. And 9, total cost of 9 is not better than the cost of 8 of reaching B, right? So I leave that 8 alone. I don't update this 8. Just leave that alone. Make sense so far? So far, so good? Okay, now let's continue. Oh, okay, so why is this? So can I ask you, why is this edge dashed here?
Because it's not the least, how can I say it, like
Yes,
the fastest.
not,
It's like the
we're not
worst.
going to use this. By the way, these dashed, later we'll talk about something called the shortest path tree of this graph. So these edges will not make it to the tree. So, but that's like heads up. So we will never use this edge again. This edge will not be used to construct shortest paths later. Okay, so this is what we have. Now, what's the next step? So we're continuing with these steps of the algorithm. What's the next step? The next step is to peer out of C and see where we can get to. We can get now to these new vertices, E and F. Okay, so these are the costs. We update those infinities that we had before, that 5 and 11. So we have that. So now we have new costs, 11, 3, 5, and 8. So what do? What's the greedy choice that I was making in this high-level discussion that we had before, this kind of vague discussion that we started with? So what do I add to this? So again, I'm expanding the set S, right? So I'm adding a new vertex to the set S. So which of these vertices will go to S? Will go onto S?
D.
Yes, D is the smallest of them all, right? So D will be consumed by the cloud. So let's take a look. So here's this D is in the cloud. So now, okay, so now we have new ways of reaching F, and well, there's no new way of reaching E. So, but there is a new way of reaching F from D. What's the cost of the new way of reaching D? So before it was 11. How did I have this 11? How did I get this 11? It was this path for 2 from A to C and then from C to F. Before, this was before D was added to the cloud. But now I have D in my cloud, so I can consider the edges emanating from D as well. Before it was a blue edge, but now I have this is a red edge, so I can consider this edge. Okay. So I'm considering this edge here. It's a cost, it has a cost of 5, that edge. I had a way of getting to D at a cost of 3. So 3 plus 5 makes 8. And the thing is that 8 is smaller than 11. So I erase this 11. So the 11 that I had before, I erase that 11 and put an 8 here. This is my cost of getting to F now. This is my update of the cost. I don't yet know that this is an optimal way of getting to F, but it's better than what I had before. Now, when I add this F, whenever it will be, I add at some point, I will add F to my ever-growing set, cloud set S. At that point, I will declare that I know the shortest path to F. But as of right now, I don't know. I just have a better estimate of getting to F. Okay. There are no more updates at this stage. So what do I do next? Again, so we're the next iteration of the algorithm, I'm expanding my cloud S. So what goes onto S again? What goes onto S?
F.
Yeah, F has the F. Why F?
Do we start from the last vertex that we stopped, or
We'll
we
look at
check
everything. We're peering out from S. And
Okay, then
looking-
E.
Yeah, so the shortest is E, the smallest. So we're making this greedy choice, right? So now we're going to consume E because it has the shortest number attached to it, label, the distance of getting, the cost of getting to E. Okay, so E is going to be included. So here's E. And now I'm looking outside of S again and updating my estimates to other vertices. Okay, so notice, like, I don't know what the path of what's the best way of getting to F is. I knew that to B, before I could get at the cost of 8, just straight from A. This would cost me 8. At some point, the algorithm considered this path, but notice that one of you mentioned, am I looking at the combinations of all paths? And the answer is no for this reason. Notice that when I eliminate these 8 edges, I'm not considering those paths anymore. So for example, this path, there's no need to further consider this path because this path has a cost of 9, and I already know a shorter way of getting to B, right? A shorter way of getting to B. So this path will not be considered. But now notice what's happening. Once my cloud has consumed the vertex E, I have a new way of reaching B. A new way of reaching B. What's the cost of the new way of reaching B?
7.
It's now 7 because I could reach E at the cost of 5 and then plus 2 here. That's 7. That's certainly better than 8. So now I eliminate this path. It's become dashed, right? So this edge will no longer make it to the final shortest paths tree, which we will define in a few minutes. This edge will not be used in the roads, in the shortest roads of getting from the source to anywhere else, in fact, not just to the final vertex F. Okay, so now what's the next step? So now help me out.
We look at outside the set again at the 2 vertexes left, and we choose B to include because it's 2.
Yeah, it's exactly right. It's exactly right. You peer outside of S and pick the smallest one. Greedy choice is to include B. So now your S has included B. Okay, so now this S has grown here. Now at this point, I have estimates. We've had it for a while, estimates to every vertex of the distances. But so the algorithm keeps running until we're able to include every vertex into S. So far, we have like 5 out of 6 vertices in S, but we need to add F. So at this stage, well, we will be adding F, but the question is at what cost? And it turns out that, the cost doesn't change of reaching F. It's still the same. We have the best way of reaching F is at the cost of 8, and that is to go through D. So there's one vertex to pick, so we pick it, and now we're done. Why are we done? Because we've included every vertex in the in S. Now notice that what we've ended up with. You see these red edges here? So if you redraw this, A, B, C, D, E, and F. Okay, so just redrawing the vertices. If you just draw the edges, these guys, this, what is a tree, by the way? What is a tree? What's the definition of a tree? This is a tree, for example. This is a tree. Tree built on the original graph. Now, a tree is simply a connected graph that doesn't have cycles in it. This original graph has a bunch of cycles in it. This is a cycle. A tree cannot have cycles in it, and it's connected. That's what a tree is. It's one definition of a tree. So here's a connected graph that has no cycles in it. It's a tree. This particular tree is called the shortest paths tree. We've reconstructed this tree. Well, we constructed it from the original, based on the original graph. Okay, I still have all the same vertices, but now if you annotate this tree with the costs of getting to them, which we keep track of as we run the algorithm. Okay, so what we have is pick any vertex that you'd like, and let's say F. Then I have the shortest path from A to, by the way, in a tree, there is a unique path from actually any point to any other point, okay? Or if you designate one node or vertex as special and call it a root, there's a unique path from that root to any other node in the graph. So in fact, between any 2 nodes, okay, you can designate any of these vertices as special, but between any 2 nodes, you have a unique path. That's what makes tree special. In particular, from A was our original source vertex. You can get anywhere. So for example, if somebody asked you, once you have this tree, once Dijkstra's algorithm computed this tree, that is, just drew this somehow, represented it inside its memory, then you can ask it, what's my shortest path to like vertex B? And Dijkstra will tell you, don't take this road. you will be stuck in traffic there forever. It will tell you that's a cost of 8. Take this road, go to C first, and then E, and in your own merry way, put your favorite music on, and you'll be there in no time at a much lower cost of 7. And you won't have to go through this anxiety-inducing traffic of A to B straight route. That's what Dijkstra will tell you. And that's how it works. Okay, now I haven't given you the pseudocode, but strangely, I want to go through another example before giving you the pseudocode. And this time, I'm going to run this example. Let's do this one. Or maybe there's, I have a very detailed handout about this one. Maybe we'll do it the next time. Let's do this one. It's a small one. So we'll start small. This is how you will write up your solution on a quiz to a Dijkstra's algorithm question, right? So obviously, if your life depended on it and somebody just asked you what's the shortest path from A to E, you will just examine these paths. It's a tiny graph, so you'd find the shortest one. That's not the problem. The point is to run this algorithm, to run Dijkstra's algorithm and fill out a table. What table, you say? And so let's see. In the table that you'll be filling out, when you see a question like this, you'll have these vertices A, B, C, D, and E listed as like the heads of these columns, okay, in the table. And then you have this vertex S. I'm sorry, the set S is here. Let's make that blue. This is your cloud that was initially empty. And now when you start running Dijkstra's algorithm, you will be attaching distances, the shortest paths, to each of these vertices and placing those distances in a row, and then picking the best vertex and adding those vertices to the set S as you go along. Okay, that was a mouthful. Now let's run. So here's what we do. I have my table set up. What I do is at the initialization step, I assign the distance of 0 to A. Let's go with black here, 0. And then infinity to everybody else. Every other vertex gets an infinity. Then I look at each row and pick the entry that is the smallest. Here, this is where I'm making the greedy choice. Pick the vertex that has the smallest, that has the smallest value in each row. And by the way, mark where you got there from. Let's use red here. You got there from A, like A to A. A is the source. A is source vertex. So you got from A to A at the cost of 0, and you add this A to your special set S. Why? Because it was the smallest one in this row. So every time you pick the smallest one, put it on S. And here I'm going to mark this circumstance here that I've just included. This is my ever-growing cloud. Okay, you don't put this on like in the quest, you don't have to put this, but I'm going to cloud S. This is my cloud S. So far I just have one vertex in this cloud. Now I'm going to peer outside this cloud. So I'm sitting in this cloud. So imagine you're inside the cloud. You get to survey the vertices already in the cloud and look at everything that you can reach from the cloud. And mark the distances to every other guy that you see from the cloud. Okay, so what do I see from the cloud? So I see this dude from the cloud, that's B. And I see this dude from the cloud, his name is C. So first, I ask B, what's the distance of getting to you? Initially, my distance was infinity. I had no idea how to get to B. But now from the cloud, I can see B. And I know that at the cost of 10, I can get to B. If I had $10 in my pocket, I'd get to B. Okay, so I erase that infinity here. So maybe I should mark here these. Initially, the costs, these infinities are there. Now I've erased this infinity. And the cost of getting there is 10. So I put a 10 here as a cost of getting from A to B. Okay. Then I look at C, and I had a cost of infinity of getting to C, which I erase. and put the cost of 3 there. So I put down my 3 here and I mark it that I came there from A. Okay, so now there's no way of reaching any other vertex. I have like from within this cloud, I do not see D or E. I only saw B and C, and I've updated their costs. And because I don't see anything else, these infinities I just carry over. Just copy them. Now I'm making the choice, the greedy choice. Here's where I'm making the greedy choice. Pick the smallest element in the row. All right, so what's the smallest element in the row? What's the smallest here?
C.
Yes, C is the smallest element. So here I include C onto, and I put it onto my S. So once I put it on the cloud, this blue thing represents the cloud. This blue set S represents the cloud. So I put a C there. Now, what do I see from the cloud? Now my cloud has become bigger. So maybe I see more vertices from my cloud. Well, yes, I do see D and E now. I couldn't see those guys before, but now that my cloud is bigger, I have more territory to cover and peer out from. So now I can see D and E. Okay, great, you say. What's the cost of getting to E? Well, it was infinity. And what's the cost now?
2.
Sorry?
5.
It's 5, 3 plus 2, exactly, 5. And I got to E now at the cost of 5 from C. Okay. Now, I have a way of getting to D. What's my best way of getting to D? Well, it was an infinity. But now what's the cost of getting to D?
11.
11. And I got there from C. Okay. What happened to the cost? So let's erase that and put there an 11. With B, nothing happened. So I just copy this guy, the B.
Doesn't it change now?
What
Because
B?
it's
Oh, yeah. Yes. So what's
to
happening?
7.
Oh, okay. So what's happening to B? I have a way of getting to B. I almost made it.
7.
Yes, I have a better way of getting to B also. Right. So notice that I have a way of getting to B at the cost of 7. So I erase the 10 that I had before, and I put there 7. And I change this entry and say that I got there from C. Okay.
This we only need that for if we had to do the tree path, though, right? Not for this specific example. Or you want us to update every single step? You want us to update the shortest path?
No,
Because
the
right now-
algorithm does this. I mean, what do you mean? Maybe I'm misunderstanding.
Because right now we only need to find the shortest path from A to E, right? Because it says
Yeah.
destination.
Uh-huh.
Are we gonna stop there, or we're gonna
Oh,
expand the whole
good
set?
point. So here's the thing. It turns out that the state of the art today is that when you run the shortest path from A to this final vertex there, if your cloud S has included all the vertices of the graph, then you will have the shortest path from A to every other vertex in the graph. You cannot help but solve a larger problem than you set out to solve. Initially, you just wanted the shortest path from A to like T, from start to end. But you actually will have the shortest paths from from the source vertex to every other vertex in the graph. And because we're keeping track of all these vertices here from where we came, these like, okay, so how we got to that vertex at each stage. That the reason we're doing this is we will be reconstructing that tree that helps us reconstruct the shortest path tree from the source vertex to every other vertex in the graph, not just E.
And
Now, that's yes, please go ahead.
Oh, and I said, and so we're just gonna get like all the shortest paths in general because like ideally we're never gonna know how big the actual graph is. Like there could be some long path to E, so we have to just find all the paths in general, right? So like you have to find the shortest path to every vertex because like looking at the graph from the paper, we can see the shortest path, but in reality, like there could just be like long numbers and larger numbers of paths. So you have to check to make sure all the different paths.
Yes, that there are usually many paths, right? But did you notice how the algorithm keeps eliminating some possible paths? So we're not actually not looking or some paths that along the way will not be the shortest ones.
Oh, yeah. Okay.
Right. So just as before, these guys that we eliminated, I mean, if we left them in there, and this is not how the algorithm works, but if we left them in there somehow, then we would be traversing those, we would be taking them into consideration, because using those edges, you could make a path from the start vertex to other vertices, but we're not considering them. And this is actually saving us a tremendous amount of time.
Oh, okay.
Right.
Yeah.
So we'll keep addressing those questions as well. So for now, what's happening here? So yes. So okay. So what was it? Yeah.
So and then also just like when we're like writing this down, so since C can't go back to A, we just leave it blank. Like you don't want us to put like anything there at all, like just to show it.
C no.
Because C can't go back to A. So
yeah, that's a good point. So C cannot go back to A. Once you've put the vertex on S, on the special set S, you're done with those vertices. You're never going to be reconsidering them again. So that's one of the things that we have to prove about this algorithm, that it maintains this invariant that we call that when you add something to S, you know the optimal way of getting to that vertex in S, any vertex in S. So you never have to reconsider any of the vertices in S, although there may be so you could have like a second edge coming back from C to A, at whatever cost it is. Once you've added C to S, that's it. You would not be considering that edge as one of the possible paths in the final shortest path. That edge is not going to be on that path.
Okay, thanks.
And that's something that needs to be proved. We haven't proved it, but I haven't even written down the pseudocode yet. So but we'll get there. Okay. All right. So what I should have circled that maybe, but now, okay. So what's happening now? So what's the next step?
We're adding E to S.
Yes. So we've just included. We're now including E. Why? Because it is the smallest here, smallest entry in that row, and therefore I'm writing down that E now is going to be included in my S. Okay, that's great. So now I'm peering out of my cloud again. Is there a new way of reaching? Well, there's no new way of reaching B. Okay, I'm not updating that. Is there a new way of reaching D?
No.
Well,
there is, but
yes.
It's not. We don't.
Yeah. So let's talk about that. You're correct. We will not be updating it. But what does the algorithm do? What does it compare to what? So it looks at it. Yeah. Yes. Go ahead, please.
It looks the path from E to D, and it says that it's right now it's 40. It's going to be 14. And it's more than 11, so we don't consider it.
Okay, does everyone see this? So right now, the cost of getting to E is 5. I know that. To get to D, we need an additional cost of 9. Incur this additional cost of 9, which adds up, 5 plus 9, which adds up to a total of 14. But currently, I have already a way of 11 of getting to D, okay? Which is through C like that. So I already have a better path. So that path from E to D will no longer be considered. Does that make sense? So I will not be updating that path. So what happens is I just carry this over and still say that I came there from C. I'm not updating that. Well, do I have a new way of getting to B? No. So I copy that as well. So Sev 7. And that was how I got there was from C. So that's it. Now what's happening next? So notice this is my cloud keeps growing. So again, at every step, and here comes the next step, I will be adding some vertex to this cloud. So this cloud is consuming the next vertex. Which one is it?
B.
Yeah, it's B now. So B gets consumed. So I pop this off and say that B has just made it to my special set S. Okay, now what's happening?
We're updating D to 9
from B. Now, okay, so let's not jump ahead. That's correct, but I'm peering out of my S, set S, and I'm seeing that there is another way of reaching D now. Now this time it's from B. Now because B has made it to my set, I can look from B, and there is a new way, a new road somebody just built from my cloud, apparently to D. And that's at an additional cost of 2. That hop itself is at an additional cost of 2. Well, the cost of getting to B was 7. 7 plus 2 is going to make 9. So I erase my 11 and place a 9 there. So I say that now I have a better way of reaching that from B. Okay, everything else I don't copy. Okay, so that's it. There's nothing else I could see, nothing new I can see from my cloud. So what's the next step? I look at this entry, this row. In general, I have a bunch of numbers, but this time I'm down to just one number. So I pick the smallest. What's the smallest of all the numbers? It's that. So now finally my D makes it to the cloud and I consume it. And now I'm done. Now the algorithm completes. Why does it complete? Because S, which was initially empty, this guy, now contains every vertex in the graph. And I get all the vertex distances now. I've got them annotated with the proper shortest distances. And I knew those distances, these annotated labels, these labels for the vertices that are the distances. I knew these are the best because, once and we haven't proved this, but once I put the vertex on the set S, it is optimal. That's it, we're done. Something that needs to be proved later. Any questions? This is the way of writing down Dijkstra. Dijkstra's run. Okay. Now, I guess we'll, okay. Okay, so I should tell you, well, the answer is on the next page, but, okay. So, and the last thing that I want to tell you is that we have let me write down these now, why did we keep track of the vertices from which we came to each vertex as I was putting them on the set S? To reconstruct the shortest paths tree. It's usually the question after you've run Dijkstra's, what is the shortest way of getting from A to everywhere else? And how will I know? Just by looking at the tree. How do I build the tree? I reconstruct it from the run of Dijkstra's algorithm. I look at any entry, and by the way, these don't have the sequence in which the vertices were added to S is this, okay, from top to bottom. This is the sequence. But, okay, so let's look at D, although we don't have to look at them in any order. You can look at any, let's look at E actually. So what's the best way of getting to E? What's the best?
From C.
Yes, so I'm making this hop from C. Apparently this is how I got to E, and the cost there was 5. So I annotate E with a 5. Okay, let's look at any other vertex. Well, okay, let's look at D, fine. So D, I got there from B. So apparently it looks like that. And the cost there was 9. Well, okay, how did I get to B? So B was added like almost at the very end, but how did I get to B?
From A.
From C.
From C. From C. So I add this edge.
So we basically go back until we get to the source.
Yeah, so we need to reconstruct the whole tree. So this has to be a connected graph on the same set of vertices. It will have no cycles. It's going to be a tree. It has to be connected. So what's the way of getting to B? So finally, we need a way of getting to any vertex. So I'm actually not done yet because I need a way of getting to C from the source and to B from the source. So let's start with C. What's the way of getting to C?
From A.
A.
From A, at what cost?
3.
3. And, yeah, and how did I know this? You told me, but I could have also looked at this table, right? So, and I look at the entry for C, and I look what I popped off this row to add C, and looks like it's this entry, and now I have an annotation. I got there from A, so that's why I put this edge from A to C here. Finally, I look at, well, we looked at every vertex, actually. So we looked at B, what's the best way? We already talked about this. Okay, it's from C at the cost of 7, so here's the here's this is the tree. There's a unique path now from the source vertex to any other vertex in this graph, and that's how to get to that vertex from A. Okay, so that's it. So we'll pick up Dijkstra. We have to talk about pseudocode. We'll have to talk about the properties of Dijkstra. Why does it work? But this is the algorithm that lives in your GPS. With minor adaptations in code, it works for both directed and undirected graphs. So sometimes you'll see a question with a directed where this one happens to be directed. We can do it with an undirected graph somewhere there. Like, I don't know, we'll do it next time just for practice. And yes, I'll post the slides. And note also, please, that I've posted some extra practice questions there. And please do those, right? So let's end this recording, and I'll post the recording later.